Welcome back to the second half of the lecture about P2P video streaming. In the first half of the lecture, we already discussed the fundamental knowledge about different approaches in the P2P video streaming and also other solutions like unicast, IP multicast, and content delivery networks. Especially in peer-to-peer video streaming, we classify the systems according to the type of topology, which are either trees or mesh, and also the way the video packets are disseminated over the connections, which is either pull-based or push-based. And subsequently, we classified three types of systems: so pull-based systems, push-based systems, and hybrid systems. We also discussed the drawback and advantages of each of the types of the P2P video streaming systems. Now, in the second half of the lecture, I will describe three exemplary systems for each of the types. First of all, let's have a look at a push-based system with split streamed. So the system was proposed in 2003, and the goal is to establish a multicast tree and to balance the load between different peers. So meaning that peers, so no peers should upload much more than other one. Now, if we recall the single tree topologies that we discussed some time ago, so the peers which are very close to the source of the stream has to upload to several peers, but all the peers at the leaves don't have to upload to anyone, and therefore it's not fair. So in split streams, it aims at fair load balancing, and also by the goal of split stream is to achieve robustness against failing nodes. And the approach of split stream is to build multiple trees. So instead of one tree, split stream builds several trees, and then to keep the inner nodes of all the trees deep joined, meaning that so one node forwarding the video packets in one tree will be receiving the video packets in all other trees. In other words, there should not be any node that sending video packets in more than one tree. What is the reason for that? So the reason is, if one node sending video packets in more than one tree, meaning that many other nodes will depend on that node, and when it leaves the system, the whole system will be highly affected. So how split stream implement its concepts? So first of all, the whole video stream is divided into stripes or partial streams. Let's have a look on the right hand side. Here is the original video stream consisting of video packets numbered from 0 to 9, and stripe number 1 will consist of all the video packets with odd sequence number, and stripe number 2 consisting of packets with even sequence number. So the consequence of this is that if even for certain reason, one stripe is so the particular peer doesn't receive video packets of a certain stripe, it still can have the packets from the other stripe in order to recover the video. And the result of the whole system is multiple trees, or the forest. So let's have a look at this example. Here we have one source, number 1, and 7 other peers. The whole video stream will be disseminated over 2 paths, right? With stride number 1 over the black links and stride number 2 over the red links. So first have a look at the tree which is used to deliver stride number 1. So from the source we build one delivery tree or multicast tree to 1 to 2 and then to 3 and 4. From here number 3 folding to 5 and 8, and then from the 4 folding to 6 and 7. Stride number 2 is forwarded in another multicast tree, so from 1 to 8, and then from 8 to 5 to 3 and 2, and also from 8 forwards the packet to 6 and then to 4 and 7. So if we have a look and check the condition about inner node disjointness, we will see that the node number 2, for example, is forwarding video packets in the black tree, and it receives video packets in the red tree. Similar we can also find for other peers. So for splitstream, in summary, splitstream achieves fair load balancing. It is robust to departure of nodes for the reason that I described before, because the node only forwards the video packets in one tree. However, splitstream also has several issues. The first issue is about the heterogeneity of nodes, and the second issue is about the unbalance, and the topology is also fragile when peers join and leave very frequently. And the third issue of splitstream is that the trees can be very high. Why? There's no optimization of the tree to make it flat. What is the consequence of a high tree? It's long latency, and also it is unbalanced between between one tree and another, meaning that video packets of one tree have a longer delay than the other tree, so making the node has to wait for all the packets in order to decode, and then the latency fluctuates. For now, let's explore one representative of pool-based systems. We will explore DONET, the protocol implemented in many P2P video streaming systems, such as PP Live, Cool Streaming. So the basic idea of DONET is data-driven. So let the data, the availability of the data to guide the flow of the video streams. And therefore, if we look at the figure on the right hand side, here we talk about the pool-based system with a mesh overlay, and therefore all the participating nodes or users establishes the partnership relations. They form some kind of mesh with bidirectional, so data can either come from one peer to another and vice versa. So the basic idea of this kind of system is that each peer has to send data informing its partners about which packet it has and which packet it doesn't have currently in the buffer. And based on the information collected from all the partners, each peer will decide from where it requests the video packet, which is a scheduling problem. Now, the components of DONET consist of, first of all, the membership manager. So the goal is to maintain the list of all the active peers in the system, and the list is updated via gossiping protocol. So periodically each peer will send a message to all the neighbors telling, okay, I'm active or I'm online. Then based on the information from the membership, some of the members in the whole membership will be selected to be the partners of a peer, and all the partners will exchange with one another the buffer maps, which consist of the information about the availability of each video packet in the buffers within a certain windows. Now let's have a look at one example of the buffer map. So here is the timeline, and we have the buffer map of certain sites. So 12 video packets inside this. Here we have the buffer head, which is always the newest video packets, and here are all the video packets, and the package which is already available in the buffer will be marked by 1. So this bit is set, and similarly the video package which is not available in the buffer will be set as 0. So by receiving the sequence of 1 and 0s, the peer can figure out which packet is available, which packet is not. And finally, from those information, peer will run the scheduling algorithm to determine from which partner it should request which packet. The implementation of DONET first of all consists of the unique ID for the membership. When a new peer joins the system, first of all it will contact the server to get a random list of nodes, from which it will contact and get a list of the active peers in the systems. I call this as a mem cache or membership cache. The membership information are gossip, or in other words are forwarded among the peers in the system. The goal is first is to inform the other that a certain peers is available, and if after some time out if a peer doesn't receive any updated information from a certain peer, then the peers will be removed from the membership cache, and the peers will request for a new member. The video streams is divided into equal size segments, and normally a buffer consists of 120 segments, and each segment represents for 1 second of video play out. So one important part of DONET is the scheduling algorithm. The goal is to adapt with the network dynamics. Why is that the case? Since the request for video packets coming pretty randomly from all the partners, and each peer has no control of that. What it has the control of is how to respond to those requests. And the more upload bandwidth a peer has, the more likely that it can respond very quickly to the request. Here we have we need to notice that each video packet has a certain playback deadline, because we are talking about live video streaming. It means that if a video packet comes late after the deadline or after the playback deadline, then it is useless. And therefore the goal of the scheduling is to minimize the number of missing packets to the deadline. Since one particular peers have to request several partners at the same time, the problem is similar to a parallel machine scheduling problem, and therefore it is NP hard. And in the presence of peers dynamics, joining, leaving all the time, the problem is even more difficult. And therefore, in order to relax the problem and to solve it, DONET introduces a simple heuristic. So the heuristic used by DONET functions as follows. First of all, a peer will select the partners which has the rarest packet. Why is that the case? First of all, if we don't select that partners which has the rarest packets, peers cannot request those rare packets from anywhere, so it has to request. And the second reason is that by requesting the rare packets right away, so the chance that the packets will be more available within the system will be increased, and thus helping the dissemination of those packets amongst the peers. The next step is to identify the video packets which are available in multiple suppliers, and then select the partners with the highest bandwidth available. How DONET can recover from failure? First of all, for departure, DONET employs a graceful departure. So a peer will issue a departure message so that its partner is notified, and then can request new partners, and then also to refresh the membership cache. It is more challenging to deal with node failure, because in this case there is no graceful departure message. However, DONET implements a timeout mechanism. So after a certain amount of time that a peer doesn't receive updated message from its partner, then that partner is considered to be failed or to already left the system, and then it will remove the partner, request a new one, and also update the membership cache. So in summary, Donut is widely implemented in many peer-to-peer video sharing systems, and the main components of pool-based system, especially in this case Donut, is to use a tracker or maybe distributed membership cache, and also establishing partnership relation between the peers, exchanging buffer map messages, and then based on the information from the buffer maps collected from the different partners, each peer will run the scheduling algorithm to decide which packet it should request from which partner. Now let's have a look at M3 bond, which is one representative of the hybrid systems. So hybrid means the combination of two types of topology, tree topology and also mesh topology, and also the combination of two ways to disseminate video packets, pull-based and push-based. So the goal is to combine the advantages of both systems. So the new idea in M3 bond is to identify and to use stable peers, and then among those stable ones, establish one push trees, and the tree will be on top of the mesh topology. So here the mesh topology will provide like connectivities, and then the tree topology will provide the low latency and efficiency to disseminate video packets. The motivation for this kind of design comes from the measurement of running peer-to-peer video streaming systems, BB Live. So here we have in this plot on the x-axis, which is the percentage of the end-to-end connections, and here on the y-axis it is the percentage of the video packets delivered. The interesting here is that 80% of all the delivered video packets is done by 20% of all the connections. It means that the small number of connections that are more important than others. And if we can identify those connections, we can establish the tree over them. So the architecture of M3 bond, so first of all, it should consist of all the stable peers, and all the non-stable peers will be connected to the outskirts of the trees. And then for the data, mainly it is pushed among the stable peer, and it is pulled from the outskirts. So first of all, the mesh will consist of all the nodes. So the reason is that any peers, stable, unstable, will have more than one connections. and therefore the connectivity will be maintained. And then all of them will also exchange the buffer maps, even though they are not use information of buffer map to request the video packets right away, but only as a backup. I will explain more about this later. The construction of M3 bond is the following. So first of all, it has to promote the stable peers, right? So how to identify the stable peer? So M3 bond defines stable peer as the one that the time that it spent in the system exceeds 30% of the total session, video session. And then in the bootstrap, each peer will receive the length of the session from that moment to the end, the arrival time, and then a partial list of the partners, including some of the 3 bond nodes. And then using those, it will connect to the match partners and then to request the packet. And then periodically, M3 bond will check the ages of each packet of each of the partners, and then promote those peers, and then promote themselves, I mean, as stable peers. So now, once the backbone of the overlay is established, there's several ways to optimize the topology. First of all is the high degree preemption. Let's consider this example. We have Y forwards video packets to X, and in turn X forwards packets to some of its child nodes. And then each node periodically checks if it has the less number of child nodes and so closer to the source. And in this case, Y has less number of child nodes. If we keep this that way, we have all those child nodes of X which suffer from higher latency, right? So here 2 hops, at least 2 more hops. So by applying the high degree preemption, X will preempt the position of Y, because here X we can reduce the overall latency for X and also its child nodes. And then in one of the child nodes of X, we will attach Y. So in this case, X will go up, Y go down as a child node of X. The second optimization is low delay jump. So each node, in this case X, will periodically check to see whether it has the lower delay. So in this case, Y has a lower delay than X, and also Y has enough bandwidth to accommodate X, and therefore X can directly jump to Y. So X will come from here to over there, and therefore both of those nodes will have less latency and also shorten the tree. So regarding video packets dissemination, we have the switch between push and pull. So basically the main request, the main dissemination method will be push based for all the peers in the backbone of the tree. So here we have a timeline, and always we have newest packets coming over, right? Coming here, 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 here. However, we also, each peer also maintain a windows, and then within this windows it can see whether any packets is missing. Missing could be that the packets arrived late due to the bottleneck in the upload bandwidth or download bandwidth or congestion and so on, and in this case it will trigger like a request. In order to deal with node churn, so there are also two ways. The best would be to receive the graceful leave, so inform the neighbors and also own the child node that okay, I'm leaving, please connect to this one as an alternative partner and so on. And regarding the failure, it is detected by control or signaling messages. In summary, we have explored different types of P2P video streaming systems. The first type is push-based. Here, all the peers maintain three topologies, and the video stream can be also split into multiple substreams or bytes. The advantages of push-based system is low delay, low overhead, but it suffers from the robustness. On the other hand, we have pool-based systems, where all the peers forms bidirectional connection with one another to form a mesh topology, and therefore from one peer maintains several connections to all others, and the connectivity is maintained very highly. The advantage is the high robustness. It's very difficult to isolate a certain peer from the system. However, the drawback is the higher delay, because video packets has to be requested, and before that peers has to exchange the buffer maps. Also, the messages of the buffer map causes the high overhead. To combine the advantages of both push-based and pull-based systems, hybrid systems were proposed. The basic idea is to use a mesh topology, and on top of that it maintains a tree backbone by identifying stable peers. And the consequence of that is the hybrid system can deliver very low latency and also low overhead. It can also increase the robustness. However, the backbone is still fragile. So when we look at P2P video streaming systems, now after 20 years since it was the first one proposed, we see that there are some failures. For example, BitTorrent Live. So starting from BitTorrent, a file sharing system, BitTorrent Live was designed and was launched with the goal is to guarantee a delay of 10 milliseconds when stream the video over the internet, which is a really good considering all the complexity of the internet. Unfortunately, after like 1 year launching the systems, it was closed in the summer of 2017. We also have some systems moving away from peer-to-peer streaming paradigm. For example, the iPlayer from BBC, so moving from peer-assisted model into completely centralized. Nevertheless, there are also success stories for peer-to-peer video streaming systems. One of the example is PPTV in China with 400 million users. Another example is Zatu with 20 million users, mainly in Germany and Switzerland. So for now, I'm finishing my lectures about peer-to-peer video streaming systems. For further reading, you are welcome to have a look at the background. This is one survey paper with all the overview about different kind of peer-to-peer video streaming systems, and for particular systems that we already explore in this lecture: split stream, DONET, M3 bond. Here are the papers with all the design and implementation.